Hello everybody, this is Todd Frazee and this is the video tutorial for the TCOSE-03 CAM tutorial. This part is a sheet metal part and we're going to be making a foray into creating toolpath for Waterjet. The commands we use are similar to what we would use for any center line cutting tool that uses a beam, like a laser, Waterjet, plasma. The principles are the same, you just have to set up the nozzle tip diameter for the offset of the particular tool you're using and select the correct post processor. And we will go through all those steps in this tutorial. So first we're going to bring up our model in, you're going to open the TCOSE-03 model. I'm going to go ahead and minimize the data panel so we have plenty of space here. Okay, we've opened our file, our -3 file, and it's a sheet metal part. So to support the manufacturing side, we have to create what's called a flat pattern. And the unfold command is only for modeling purposes. The flat pattern is a support manufacturing. So it creates an actual extra entity here on our feature tree. You're going to go to the sheet metal, create flat pattern. You're going to pick on a neutral plane just like you did with the unfold command and select OK. And it's going to enter a mode similar to sketch mode where you can change the flat pattern itself. And what it does is it puts in the bend lines where you would actually bend the part, and those go in as these phantom lines and flattens the part. We don't really have to do anything to it, so we're just going to hit finish flat pattern. And then what happens is a flat, here's, you can see the flat pattern feature showed up on the feature tree below document settings. If you want to go back to the flat pattern mode, you just select the box and you go back into it. So we're going to hit finish flat pattern. And it's always a good time to save when you're switching modes. And then we're going to switch to the manufacturing workspace. We want to make sure our units are defaulting to inch in the manufacturing workspace because our equipment's running in inches. And the model, when you're in this mode, will be all in inches. Okay, so once we're in manufacturer mode, you need to expand the models tab. And embedded in it is the flat pattern. So we want to activate the flat pattern. And it shows it in a flat state. And it defaults to throwing an X, Y, Z plane like shown. And we now can start working on the toolpath. So the very first thing you do in any of the manufacturer steps, no matter what mode it is, you're going to create a setup. We're going to click on setup. And we're going to make sure we're in fabrication mode, because we're going to be using this cutting command. You're going to go to the pull down menu under setup, and we're going to create a new setup. Now there's various parameters in here that are going to set up the stock and your origin and the naming of your program that you're actually going to run on the machine. So the tab order on this to me is not intuitive. It seems easier to me to start on the stock tab because some of the selections under setup are dependent on the stock tab. So go to the stock tab first, and we're going to set the material size that we're going to start with. So we're making this part, but we're going to make it out of a larger piece of material. So assuming we're just going to cut one of these and we have a way to clamp around the edges or hold it down with weights, our side offset, we're going to leave a ½ inch of margin around. Now if you were obviously cutting multiples of these, you might use a different scheme, but for the purpose of this demonstration, we're going to put a ½ inch margin around the outside edge. And we're going to start off with material that's on thickness. We're not milling it down this thickness with this type of process. So our stock top offset is going to be 0. It's going to be the same thickness as our model. So this is automatically taking the extents of our model and offsetting for us. Okay, so that's all you need to set for the stock. We're now going to go back to the setup. We need to choose our orientation on the machine and our origin. It allows you to move the origin around by selecting on these box points. So they're preset places that you might want to put your origin. For the purposes of this exercise, we're just going to leave it in the center of the stock and go ahead and leave the orientation the way it is. And what this is going to determine is you're going to need to put your shorter side of the stock along the x-axis travel of the machine, and the long direction is going to have to be in the y-axis of that machine. Alright, so we've done everything on that tab. Now we're going to go to the Post Processes tab. Now the program number here on most CNC machines is a 4-character number preceded by the letter O. A lot of the Waterjet and torch machines and flame tables and lasers, they use their own proprietary code. Some of them don't use G-code, so I'm not familiar with all the different variations of formats, but to be safe for anything with a Fanuc style controller on it, you want to keep it down to 4 numbers. And we're going to use a naming convention of 03, which is our part number, and 01, which will be our first program for that part number. And for cutting, that's the only program we're going to need. Program comment, you have more freedom to put what you want here, so I'm going to put Waterjet cutting. Okay. You could put program 1, setup 2, but this allows you to differentiate this from, say, a mill or lathe program. Our work coordinate offset, we're going to set as 1. That'll use the first work coordinate system that the machine has available. And then we're going to select OK. Alright, so then over on the left, it should start off with setup 1. Now you can rename this if you want to call it something else. But and if you goof up and you have to do this more than one time, it's going to auto change the number and index it higher. You can change it by simply clicking on it and reiterating that. Now this name will also show up later, so you do want it something that's logical and makes sense. You don't want to leave it just at default if it doesn't make sense. We're going to be generating what's called a setup sheet, and that setup sheet will display this name, and you want to be able to differentiate which setup sheet is used for which sequence of a manufacturing process if you have multiple setups. Alright, make sure your setup is highlighted, and we're going to go to the cutting option, which is the only one you have under the fabrication tab. That's the only process. It's going to open up this multi-tab window. So first tab is tool, second tab is geometry, third tab is heights, fourth is passes, and the last one is linking. The first tab is going to define everything you use with the tool. Now in the context of machines like this, it's really a tip diameter of a nozzle. And you define the diameter of that so it knows how much to compensate for the diameter of the tool. And there is also feed rate information. So it's how fast is it going to be cutting when it goes through the material, contacting what would be a finished edge. There's a lead in and lead out, which is when it's starting its cut off the material or off of your finished part. Oftentimes when a tool starts engaging in the material, you get wander of the cutting device or you get a bad finish. So you start off of in the material in what would be leftover stock and then start your cut and then progress towards the finished part. So those parameters, you can set them at different feed rates. The second tab, geometry, is selecting what you want to apply that tool to. The third tab, heights, sets all the heights for the machine. So the machine often will have a rapid rate, which is as fast as the machine will go, and to get into position, and then it lowers its head if it's capable of that, and then retracts when it's done with a process. And then there's where it's actually cutting the workpiece, where it's going to slow down and go to the feed rate that you input under the tool tab. So that's what these 3 different fields do. And then we have our passes. It describes what kind of compensation there's going to be for the cutter, what order you're going to go in, if you're going to leave stock for another process to clean up, and things like that. And in some instances, it's how many times you're going to go around the part before it cuts through. The last tab has some other parameters, like how do you treat the nozzle when it's going from finish cut to finish cut. Do you want to keep it down, or do you want to pull up and rapid lead-ins, those lead-in feed rates we were discussing on tab 1, the tool tab. Here's some parameters you can set for how that's handled. You can have it go in straight, or you can have it go in as a radius. You can modify the angle at which it approaches the workpiece, how far away from the workpiece does it start, and whether you want to lead in and lead out. There's a piercing distance. Piercing is for holes, or how far away from the part are you going to turn on the jet or whatever is piercing through the material, and it will have to do that at a distance and then dwell for amount of time and then burn all the way through the material and then start cutting horizontally. Alright, so now we've had an overview of the different tabs. We're going to go to the first one. Now the first one, because we haven't programmed anything on one of these machines yet, we need to configure the tool first before we can do anything else. So we're going to select a tool, and we don't have one currently made. Okay, so I'm going to create a new library. The library you see here displayed is attached to the current document. So any tools we make in this library, we won't be able to use on a different part. So if we're going to build a library that we want to continue to use, we're going to go to this local library here, and what we're going to do is we're going to create a new library. Select new library, and we're going to call this TCOSE. So that's for our TCOSE project as a whole. So all of the tools that we would make and use for the TCOSE, we're going to put in this container so we can pull from them again. And as we go through the program, we're going to be adding tools to this, different types of tools. Okay, and then when we're done with our whole project, we'll have a list of all the tools we need to order, or tip sizes we need to order. Will be on one list for this entire project. So once we've created the TCOSE library, we're going to go up to this icon here that looks like a little laser beam. It says Create New Tool for Waterjet, Laser, and Plasma Cutting. So we're going to pick on that, and we're going to put in a description. So I'm going to put in a description. We're going to use a small diameter tip. We're going to call this the Fine Waterjet Tip. And I'm going to put in a tip size of 0.4 millimeters. I haven't looked up the specifics on this particular tip, but if you do, you can put in your vendor information, you can put a product ID, and you can even put a URL to find the online item in their catalog. Very useful later when you're building your tool list. We're going to get into that later, but for this exercise, we're just going to leave it at this. Okay, and we're going to go to cutter, and it's a waterjet type. You can pick either laser, plasma, or waterjet. In this case, it's going to be a waterjet. Our units are going to be inches because the machine's running in inches, and our kerf width is the equivalent of 0.4 millimeters. So we're just going to put 0.4 mm. Okay, and that'll automatically do our conversion because we're in inch mode. So our tip kerf width is going to be 0.015748. So the kerf is the width of the cut that the cutter is going to leave as a cut. So if you can imagine a saw cut, if you're using an 1/8 inch width blade, you make a cut with that saw, the kerf is left by that cut is 1/8 of an inch. This is a relatively fine tip for waterjet. Some waterjets aren't capable of going this fine, but the scale of these parts we're cutting is very small, so we want to use a very small tip. Okay, and the holder tab doesn't really come into play with a Waterjet head because you don't have a tool holder. And then we're going to go to our feeds and speeds and our quality control. The machine, assuming the machine uses feeds and speeds and reads that in our code, we're going to set that here in inches a minute. Due to the size of this part, how small it is, and we want a high quality finish, I think we're going to slow the feed rate down to 30 inches a minute, and we'll do the same for our lead in and our lead out. For different processes, you may have this lead in default be slower, but for a jet process, it's not really necessary. Then we're going to go to our post processor command, and what tool number do we want to use for this Waterjet? And we're just going to leave it at a default of 1. We're only going to be running machines with one tool, mostly for this project. You would have to manually change the tip out, and so we'll go ahead and select manually tool change. And when you get into milling and lathe machines that change tools, this number would have to be unique for each program for it to know which tool to move to. Okay, so we've created our first tool, and we're going to hit OK. And it should pop up here. We got fine Waterjet tip, 4 millimeters. Okay, and the nozzle diameter in inch is displayed here. So I'll hit OK, and we've now selected that tool, and it shows up here as tool 1 with our tip diameter. Okay. So the cutting mode is have several settings, but it's really dependent on the type of machine you're using. So we're going to leave it on auto, but some of the machines you can change these quality settings and it'll change the feed rate inside the machine and ignore the settings that we're putting in here and may put in extra steps. So that you have to really reference the equipment you're using and its options for the post processor. So we've got several different quality levels which would output different feed rates. There's an etch which doesn't cut all the way through the material, so if you wanted to do some engraving, some machines aren't capable of that. And there's a vaporize, which apparently is for cutting through the plastic film that protects the material, especially if you're using the film as a masking material for like a sign making application. You might want to just burn through the plastic first and then cut through the part so that you retain your plastic coating on the outside. All right, so we've set our feeds and speeds, so the cutting rate at which the jet is going to travel. We've already set that to default for this tool, so we're going to go ahead and accept what we have there. We're going to move on to the geometry tab. Now we want to cut this part in a couple steps. If we go and cut around the outside of it, it's going to break it free, and then we won't have accurate locations for the holes. So what we want to do is we want to do two operations. The first one's going to pierce and cut the holes, and then the second operation is going to cut around the outside perimeter. That ensures nothing moves, location for when we're drilling through these materials. Now, a 3 millimeter hole, that's kind of borderline on a Waterjet process. It's possible some Waterjets may not be able to cut this round, and you might do a pierce and come back and manually drill those with a drill press, or do a secondary op on a mill. For the purposes of this class, we're going to go ahead and Waterjet it, but I just want you to be aware of that when you get the small diameter holes, Waterjet processes don't work too well, and you end up with oval shaped holes. Okay, so we're going to pick on our individual chains. We'll start with the small holes. Go to our large hole because the machine will travel over to that one, and then do our other small holes. Now these arrows can be confusing on very small features. The arrow toggles to either the inside or outside. So the large hole, it's obvious it's on the inside, and that's what we want. These, we can't really tell. And then if I flip on it, it's such a small feature that it flips on the opposite side of the hole. Because this one's on the inside, I think it's safe to assume these are on the inside, but we definitely want to double check once the toolpath's generated that it appears inside the hole and not cutting through the outside. Alright, so we should be able to leave all of these other boxes at default. We're going to go to heights, and these are defining different planes. As we talked about, the retract height is where its clearance is highest, and the head of the machine is going to wrap into that as fast as it can go. The retract height is where it may pull back to before it moves over to another feature. Now sometimes these two planes are coincident with each other, but this allows a machine to move from one feature to the other without retracting as far. The difference is you might be avoiding clamps with the clearance height, and the retract height might be while it's working within the work volume within the clamps it's already avoided. And then we have our stock top side. So where is the top of our stock, top of our material cut? And so I selected the top of my stock material, top of the model, and so that's where it's located. Now, when we set up our stock parameters, in our case, the stock was set at 0, so it's basically the same as the top of the model. So we'll leave these all at default. And then we're going to go on to passes. Now we want to default to climb cutting, so it's offset to the left. Compensation, you have two options, in computer or in control. In most cases you want to leave it in the controller because it depends on the machine that you're running. You want to be able to compensate in it. Okay, stock to leave is if you're going to do a roughing pass and you want an offset on what you're cutting for another process to remove. Smoothing is the fidelity at which the curve is cutting. So if you have this, don't have this set, you can get facets in your curved parts. For this part, we're cutting circles, so we want to turn smoothing on, and we'll just leave the smoothing tolerance at default. If you have issues with the machine not able to run that tight of tolerance, you could loosen this up. But 4/10 should give you a really close diameter circle. Now we're going to go to linking. There's the keep nozzle down, so if you didn't want it to retract to the retract plane between cuts and you want to keep the nozzle down in position, you could select that box. We're going to leave it at default. And then we have our lead ins and lead outs. Now we're doing small diameter holes, and the default lead in is almost a quarter, it's just shy of a quarter of an inch. I don't think we want it that much because it's not going to be able to lead in on these smaller holes. So instead of 196 thousandths, we're going to switch that to something closer to the hole size. So let's put in 0.040 because our holes are 125 thousandths in diameter, being close to 125 thousandths, being almost an 1/8 inch. Our sweep angle is the angle at which that lead in is going to approach the workpiece. Now we could leave that at default, but again with these small diameter holes I'm concerned about if we come in at a 60-degree angle and come back out that you may gouge your hole you just made. So we're going to set it at 90, and that way it starts at the center of our hole and goes in 90 degrees to the start of the face of the cut. Alright, and so we have a piercing clearance, and it looks like the piercing clearance is basically the diameter of our beam by default. So that's how far away from the part it has to be. I'm going to leave it at default, but I think typically you'd want that to be a little bit more. Alright, so we're going to move on to the next box. Now, positions, you could choose which hole you want to start with. In a lot of cases when you're milling or something, you might want to select an area that your operator can see. In the context of this cut, I don't think it's going to make any difference. I'll hit OK. And we've now cut our holes. Okay. So if we zoom in, you can see that there's a 40 thousandths lead in with a 60-degree angle, which I forgot to change. So it's possible that this angle could gouge into our sidewall, but we'll go ahead and leave it. Now we're going to move on to our parameters to cut the outside perimeter. Okay, so to do so, we're going to hit cutting again. We're going to leave all the tab 1 defaults alone for the tool. We're going to come to our geometry and we want to select the outside of our part. The arrow should be on the outside of our cut. If it was on the opposite side, you'd be cutting your part too small. And then we want to select, we're going to keep these others at default, and we want to select this box called tabs. And what this will do is automatically put tabs on the outside of our material so that it holds it in place. And then we can simply come back and snip these tabs off and then clean up the little edge where it's holding on. So if you've ever done any work with, say, photo etch parts or like a model kit, this would be like its sprue that holds it on, and you cut that off before you start building an assembly. So we're going to select tabs, and because this is a fairly small part, we're going to put our tabs every inch, and we don't want them an 1/8 inch thick, so we're going to, our material, that's the same thickness as our material. So let's go half of that at about a 1/16, which is 0.06. All right, so that would be the width of our tabs. And then we'll go to heights. We're going to leave all this at default. We're going to passes. You're going to leave all of this at default, except we're going to select smoothing. We're going to go to our last tab, which is linking, and we'll leave this at default, and we'll leave our lead in at the default because we are cutting the outside of a much larger part. Okay, so we got all that set, and we'll hit OK. And as you see, we have these multiple lead-ins, and the purpose of those are the tabs we wanted to leave to hold it to its surrounding material. So we'll simply snip these off, file the little tab pieces, and we don't have to worry about the part flying off the machine. Alright, that finishes the programming portion. Now we're going to go and we're going to simulate this so you can see what it looks like. So let's pick the setup so that it highlights the stock that we're starting with. It should show the origin. And then we're going to pick, and it's going to simulate everything in that setup. If you just had one of the segments highlighted, it's only going to simulate that one segment. We're going to pick the Simulate tab icon. And it's going to quickly show all of the moves. So everything that's in yellow is at rapid, the green is a lead-in, and the blue is feeding into the workpiece at their appropriate feed rates. What we're going to do now is we want to make sure that stock is selected. Now by default that's probably not selected. Make sure that's selected and it'll show this green piece of stock, and it calls it vinyl. It really doesn't matter for the simulation. And now we can play it. So pick the play button and it'll show your jet tip moving around and making its cuts. Alright, so that's your simulation, and if you zoom in really far, you can see through the part where it's been cut, where it's cut through. So these will be slugs that'll fall out, and we lead in so that we aren't damaging our part. And we hit close. Okay, so now for your assignment. The next 2 steps you would have to do before you run it on the machine. But you also want to save off electronic versions of these two documents, and you're going to upload those in Canvas. And we'll go through those steps. So you want to make sure you have your entire setup highlighted. And we're going to generate what's called a setup sheet. This setup sheet will show an image that's whatever you have displayed on the screen. So it's best practice to have what you want on the screen in the orientation you want it, zoomed in so you can see where the origin is for the setup operator to know where to set up, and a visual representation of the stock. And to do that, you have to have the setup highlighted before you do this next step. We're going to pick on setup sheet, and it asks you to pick a location to put it. It defaults to HTML. Pick my default location as where it's suggested. And what will happen is an HTML setup sheet will show up. It'll have the program comment, Waterjet cutting, and the job description is setup 1. That came from the setup name. And the document is the TCOSE-03 version 3. And the program number we put in shows up here. So you know which program this setup sheet is associated with. It will then show your image of your part for setup and a bunch of coordinate information and some information about the program itself. You got 2 operations, there's only 1 tool. Its maximum Z height is 0.06, the minimum Z is 0. And our effective feed rates. And an estimate of how long it'll take to cut this part. It claims it'll do it at 46 seconds at that feed rate. And then it lists the tools you need. So we just have 1 Waterjet head. We have the fine tip, 0.4 millimeters. So if you knew you needed to change that out, it gives the operator that information. And then it shows what each operation does. So we've got, profile 1, 2D profile 2. Now, had we renamed those when we programmed them, those names could occur there. So you might want to say 2D profile holes, 2D profile exterior perimeter. Okay, so this is a handy thing that goes in with your documentation. So you either need to save this as somewhere where you know where to put it as the setup sheet name, as HTML, and that's acceptable to upload in Canvas. Or if you have the ability to make a PDF, that's better. So there's different tools on different computers. Oftentimes you can print a PDF by going to your printer, and you might have a save the PDF, or you might have another utility that says output is PDF. And then you would save that PDF somewhere on your computer, and then you'll upload those to the Canvas assignment, which I'll show you in a few minutes. So I'm going to save this as a PDF. And in my case, I'm going to create a folder for myself for ADVM62 on my desktop. Find it easy, and I'm going to save that setup sheet. So it's setup sheet for the 0301 part. So that's the first document you need to submit. The second document you need to submit is the code that actually runs the machine. So we're going to post-process. Now, a post-processor is like a compiler. You might have heard of that term. But it basically generates the code from the programming toolpath that you made. Again, you need to have the setup highlighted. If you only have one segment highlighted, you're only going to post out the code to make that one individual segment. Now, if you notice, there's a bunch of windows here. The main thing is you need to output using a post processor for the machine you're going to run this on. So we have an Omax Waterjet. We're going to select Omax Waterjet. But if you pick on here, there's all kinds of different machines, and some of them are mills, some of them are lathes, some of them are water jets, lasers, whatever. If you don't have a post processor for the machine that you own or are using, you can go out on the web, and oftentimes Autodesk will have them out there. If there isn't one there, you can actually request that Autodesk make one. I think you have to pay for that, but oftentimes there's people out on the web that have already had that made. You're going to pick your output folder. So I'm going to go and put it in that same folder that I created on my desktop for the class, ADVM62. And I'm going to select that folder so that I know where my programs go, and they go in the same place as my setup sheets. Now the program number or name that we put in the beginning in the setup will occur here. Our program comment also came up here. Now you can edit them if you want, but it's better practice to change them in your setup. And we're going to leave everything else at default. These are some parameters that can be adjusted for the particular machine that you're doing this with for. We're going to select this OpenNC file in editor, and that way it'll pop up with the code file in front of us so we can verify that it post-processed. Hit post, pick your location, which in my case is the ADVM62 folder on my desktop. Save. And it'll pop up with the actual code in whatever text editor you have. Now, you don't want to modify it and you don't want to save it in here because you don't want to change the formatting of it. But it popped up in WordPad for me. Okay, I'm not that familiar with OMax machines. It's not using a traditional code. Looks like it uses a Excel type table, and but these are all the coordinates that it needs to move to cut the part. We're going to close that window. That's it for the cutting the part. Now we're going to move over to Canvas, and I'll show you how to upload your homework. Okay, everybody, this is the instructions on how to submit your homework for the CAM assignments. Your first one, which is the -3 part, we'll go to Unit 8, and we'll go to the assignment for the -3 CAM part. What you're going to do is you need to submit a setup sheet for every program that you did for this part, which in this case we only have one. If you had two, you would have two setup sheets. And then you have to submit the code file with the corresponding setup sheet. So in this case, we only have one, but if you had 2 or 3 programs, you'd have to submit double that number of documents. We're going to select Submit Assignment, and it'll pop up with this box down here at the bottom. You're going to choose your setup sheet file, which in my case I put it on my desktop. You want to save those in a place you can find. And I made a file for the class, folder for the class. I'm sorry, the setup sheet is going to be a PDF or HTML. And it should say setup sheet for the program and the number if you follow the instructions. Okay, we're going to select the PDF first or HTML. And it appears here. Now to add the second file, you're going to simply pick on this Add Another File. And then you're going to choose that file. So the code file for a Waterjet, our Waterjet is a .omx. If it's for the Haas, it's going to say .nc. It's basically a text file, but they put their own extension on the end. So you're going to select that, and that satisfies the requirement of your program. So you have your setup sheet and your program. Again, you're going to have a setup sheet and a program for every program you generate to make the part. So some of the assignments may have 2, 3, 4 programs. That means you're going to have 2 or 3, 4 program files and the same number of setup sheets. Let's hit open. And then we've got our two files we're going to put up. Now you can put a comment. It's kind of optional. If you have something you want to tell the instructor about your file or you had a question, you could put it there. It'll show up in the assignment comments. Once you've got those files loaded in this box, you're going to hit submit assignment. You do have the opportunity to resubmit. If you do so, try to resubmit everything that changed. On the instructor side in the grading module, I'll be able to see what was submitted on specific dates. And if I were to send you a message back saying to modify something and submit it before the due date, it'll tell me what date you uploaded your revisions, and I can see each version of the history. That's it for this tutorial, and I hope it was helpful, and we will see you on the next one.